Well, folks, good evening. My name is Professor David Jamieson. I'm a professor here in the School of Physics at the University of Melbourne, and it's my great pleasure to welcome you to our July lecture, our third July lecture for 2025. The School of Physics at the University of Melbourne is on the land of the Wurundjeri people of the Kulin Nation, who have had custody of our lands going back more than 65,000 years, and I would invite you to see the new exhibition at the newly reopened Potter Gallery featuring, I wouldn't say highlights, but the deep cultural attachment of the first Australians to this land. A remarkable exhibition. So the 2025 July lecture theme is the theme declared by the United Nations, the year of quantum science and technology. And it's the latest of the July lecture themes that have been running. The July lectures have been running every year since 1968. And I've given one or two July lectures myself over the years. Now, I normally don't ask this question, but looking around, I'm moved to ask, is there anyone here tonight who was present at the first July lecture in 1968? Oh dear. Okay, thank you for that. Now, the topic of tonight's lecture is one of the most exciting features of quantum science and technology, and I'll introduce the speaker in just a moment. But the reason why we are celebrating the International Year of Quantum Science and Technology is because 100 years ago, as of June the 25th, a young physics postdoc called Werner Heisenberg, suffering from severe hay fever in the European summer of 1925, retreated to an isolated rocky island out in the North Sea to retreat and get some relief. And while he was in seclusion on the island of Helgoland, he wrote down one of the earliest formulations of quantum mechanics called matrix mechanics. It took him 10 days to work it out, and he published a paper on this topic shortly thereafter. And this, we're celebrating the 100th anniversary of that foundational year. What happened next was a little bit uncertain. Thank you, folks. Thank you very much. So, tonight's speaker is my colleague Josh Coombs. Josh has had a distinguished career in the field of quantum computation. He's served as a postdoctoral fellow with Professor Carlton Cave at the University of New Mexico. Carl is a good friend to the School of Physics, and he's one of the few distinguished visitors that we recommended he visit the Werribee Sewerage Farm during his visit, because as Josh will probably know, he's a great enthusiast of bird life, and the Werribee Sewerage Farm is a Ramsar listed wetlands. But he's also held distinguished fellowships at a number of the leading institutions in the world for quantum computing research, including a stint at one of the front runners for the commercialisation of quantum computing, where he spent a number of years working on hardware on which you could run the all-important quantum algorithms. So, Josh, can I please invite you to take the stand and tell us all about it?
Thanks for the introduction, David, and thanks to the whole team that's behind the scenes doing these July lectures. It's pretty impressive, and I'm really excited to be here. So I'm going to tell you a bit about quantum computing, and I'm going to focus more on the hardware of quantum computing, less about the algorithms. I thought I'd put up here, I've got to get used to this. My social media, so I am on Twitter and Blue Sky. Occasionally I mostly tweet about quantum computing things and quantum computing memes, and occasionally snark about hype in quantum computing. So, feel free to follow me. So I'm split between the School of Physics and the School of Mathematics and Statistics. I only joined Melbourne University about a year and 2 weeks ago. So until then, I've been living in the US for a long time. So I think a better title for my talk would be How to Build a Quantum Computer. And over here, sorry, still getting used to this. Over here we have one of the machines that Google has built, and actually the quantum computer is way down here. This is all just wires that get information in and out of the quantum computer. And what I'd like to build up to tonight is explaining what I think is the most important experiment in quantum computing in the last 20 years. And so that's what all this is about. So at the end of the lecture, hopefully we'll be able to understand this. And I think it's really exciting that this happened this year. I've been personally waiting for this to happen for 20 years. So I'm pretty excited about that. Okay, so let's start with what is a computer? A computer is a device that accepts an input. So for example, hey Siri, navigate me to the lecture. And then it uses rules to manipulate that input, and it produces an output. And so, here's the directions from the museum to campus. And so, broadly speaking, that's what a computer is. You probably know that all computers that we have roughly manipulate zeros and ones. So these are binary numbers or bits. And so over here, I've got a red sine wave, and that's meant to represent, for example, the voice command to Siri. And I've discretized the values of that sine wave, and so it's going to take 4 levels. And so I've just arbitrarily chosen them to be 0, 1, 2, 3, representing the height above this line here. And so you can see the blue line is some approximation to the red line, and if I gave myself more numbers, I could make that approximation better and better. So over here, we have the same thing, but represented in zeros and ones. And so hopefully you can see here, 0, 0 is like 0, and then this is 1, the number 1, but represented in binary numbers. And then if I add 1 plus 1, I have to carry here. So this is 2, not 10, and then 3 is up here. So this is the binary representation of the numbers 0 through 3. And the reason why we do this is it's actually easier to represent zeros and ones on a computer. It's much more robust and makes computers less prone to noise. And we'll see a similar problem crops up in quantum computers, so we'll come back to that. So really, manipulating data is at the heart of computing. And the device we use to manipulate the data is called a transistor. And transistors are used for all sorts of things. For example, audio amplifiers that I'm speaking through now, that's built out of transistors. But for our purposes, we're going to think of it as a switch. And so here's the simplest example I can give of that is we're going to encode our information into a light. And so if the light is off, that's like a 0. If the light is on, it's 1. And so we've got a power source connected up, and if the switch is open, obviously no electricity flows through the circuit. If we close the switch, then electricity can flow through, and now the light lights up, and so we've been able to change the state of our bit. How do we do this with a transistor? So it's an electronic switch, so I'm going to draw it as a box here, and I've just drawn some wires out, and I'm going to connect another power source there. And so this is the sense in which it's an electronic switch. I need to apply some electrical energy in order to turn the switch off or on. In this case, the switch is off by default, so if I don't apply any power, the switch is open. And then if I apply some power, it closes the switch, and it can turn the light on. So this is roughly how transistors work in one of their modes of operation. And so importantly, it allows us to manipulate data. Electrical engineers use all kinds of funny symbols for these things. I'm only showing you this because it's going to crop up very shortly. So these are 2 of the symbols that electrical engineers use to represent large circuits that are composed of transistors and other elements. So transistors weren't always the thing that we used to build digital computers. We actually used these things called vacuum tubes. And so here's some different vacuum tubes. Vacuum tubes range in size from something about the size of your thumb to you can get them this large. And they were fairly common. These days, not so much. You sometimes see them in like audio amplifiers. So they were actually invented in 1900, and then from about 1940 to the mid to late 1950s, people built digital computers out of them. And the most famous is ENIAC. And so in this picture here, you can see there's basically a whole room, and this computer was built out of these vacuum tubes, and there's all these wires coming out. And perhaps it reminds you of the earlier picture I showed you of Google's device, where there was all these wires coming down. And so that's not how computers look like today. And so maybe that's a sign that we've still got some development to do in quantum computers as well. So this is ENIAC. Then in 1947, the transistor was invented. This is a replica of the transistor. This device is about the size of your thumb. And then about 5 years later, people started to miniaturize them a little bit, and you can see that at that point they were, slightly smaller than a thumbnail. So already getting much smaller, and that allowed people to build transistor computers. So they were able to swap out the vacuum tube, which was quite a large thing. It was unreliable, they broke down quite a bit, and they used a lot of power with something that was smaller and much more reliable. So here's I think this is Tradic. This is one of the early transistor computers, and you can see it's a lot neater and it's a lot smaller. So they overlapped in time with the vacuum tube computers. You can see it wasn't that the new technology, the transistor came out and we stopped using vacuum tubes. They sort of coexisted for some period of time. And eventually there were more developments. We developed different kinds of transistors. This thing's got a MOSFET. It's a certain kind of transistor. And this was invented in 1959. And this is very closely related to the kinds of transistors that are in our phones and computers today. But it took, again, about 10 years from the invention of this first transistor to the MOSFET and then, other things. Around the same time, people invented the integrated circuit. I'm just curious, have people heard of integrated circuits? Raise your hand. Okay, so maybe half the audience or something like that. So what's an integrated circuit? It's a way to build an electrical circuit in one piece of material, all out of the same stuff. And so this is a screenshot of the patent. So it was originally done in 1958, and the patent was filed in 1959. So this is Jack Kilby's patent. You can see there's some weird symbols down here. Here's two of the transistors, a resistor, so that's like a light bulb, something that dumps energy, and then capacitors, things that store energy. And this particular circuit, I think, is a differential amplifier. And so Jack Kilby showed that he could build this electrical circuit out of one piece of semiconductor, something that doesn't conduct as well as a conductor, but conducts better than an insulator. And it was just made out of one material, and he could basically build all of these things using one process. And so here's a photo of the device he made. And this is essentially what has allowed us to build the chips that we have today, the idea of Jack Kilby, that you could integrate all these transistors and different circuit elements into one material. Similarly to the overlap between vacuum tube computers and transistors, transistor computers and integrated circuits overlapped. And it wasn't until maybe the mid to late 1970s that these new kinds of transistors found their way into these integrated circuits and became more and more popular, to the point now where in many electrical engineering departments they're talking about dropping teaching the original transistor because it's basically no longer used. Although I still learned it when I went through 25 years ago. The other cool thing about transistors and this integrated circuit technology is we're able to miniaturize them, and that's part of the reason why they use less power. So in this graph, it's from Wikipedia, we're looking at the number of transistors you can fit into a square millimeter, so 1 millimeter by 1 millimeter. And you can see in, 1977 or so, you could fit 10 to the power of 2, so 10 times 10, so 100 transistors into 1 millimeter square. And then by, 2010, you can get about 1 million transistors into 1 millimeter squared. And this scaling, the fact that this data lies on a straight line, so from 1970 to the present, you see that the number of transistors that we fit into 1 square millimeter is doubling every 18 months. And this is known as Moore's law. And the scaling of the transistors per year has one of the things that really has influenced society. I think we'd all agree that the fact that, the phone I have here is much more powerful than the computer I had in primary school and high school is a very impressive feat. Okay, so the key points I want you to take away from this history of classical computing is that the information processing device we've had has changed several times over the years, from these vacuum tubes to transistors and then new kinds of transistors and integrated circuits. And it took a long time, maybe 40 years, before one won out and became the sort of dominant paradigm for the technology. And there was good reasons for that. The transistors ended up being very reliable, and we could make them much smaller, and they used a lot less power. One of the things I haven't been able to mention is that there was many other revolutions in device design, in actually building these things, in fabricating them, that I can't go into, which really enabled the technology. And similarly in quantum, we're going to have the same kinds of technological leaps in order to build a large quantum computer. Okay, so let's get into the quantum of this. People always ask me, what the heck is quantum? And so this is my best one-sentence definition of what quantum is. And it's very far from perfect. So it's the physics of, very small, cold things. And what do I mean by small? I'd say, if you think of a millimeter, we want something that's typically like 1 million times smaller than a millimeter. So take a millimeter and divide it up into 1 million pieces. And then that's the kind of scale we're talking about. We'll see that this is not exactly true, but this is my best definition of what quantum physics is. Okay, so there's some key effects that happen in the quantum world that don't seem to happen in everyday life. And I'll just highlight 3. One is superposition. And the best way to illustrate this is perhaps with an analogy to water. So if you throw 2 pebbles into a pond, you'll see the ripples propagate, and then they start interfering. And so this is a photo. This shows that at some points the ripples interfere constructively, and that means that the points where they meet up, the height of the wave is larger, and it's below the average water level. It is both larger and higher and lower than the average water level, and that would be constructive interference. And then you can have another kind of interference, destructive interference, where the water waves add up such that they cancel each other out. And so that looks like this. So this is the constructive interference. You can see that the sum of these two, that the sum is larger than either of the waves. And destructive interference, you can see these waves are exactly out of phase. The peak of this is like the minimum of this one. And so when you add them together, they exactly cancel out. That's destructive interference. So this is superposition. This is a completely classical system. You can do this in the bathtub. But quantum systems also experience this kind of superposition in a slightly different way. So that's one of the key quantum effects. Another one that I won't spend so much time talking about is entanglement. And so entanglement is kind of like superposition, but now you've got 2 distinct systems. And so I'll give you an example of that very shortly. But to give you some idea of how difficult it is to build a quantum computer, I want to take you through the wave-particle duality, which is actually maybe a little bit unrelated to quantum computing, but hopefully will explain why it's hard to build a quantum computer. The way we think about this is we're going to have a light source, and we're going to put a screen in front of it and cut 2 slits. And then the light can propagate through, and it falls on another screen. And so the light interferes and ends up making these interference fringes. So there's a bright spot here and a dark spot here. That's what these different colors mean. You could repeat this with grains of sand or a cricket ball. So you could just make 2 slots in a wall and dip your cricket ball in some paint and throw it at the slots. And it'll hit the wall at the back. If it hits the wall at the back, it leaves a mark on the wall because we've dipped it in paint. And clearly, as you throw the cricket balls, it's only going to go through one slit or another. Occasionally, they might bounce back and hit you, but it should just go through one slit or the other. What's weird is when you take quantum particles, so in this case, this illustration is about photons, but you could take single atoms or electrons and fire them through these slits. You get the particles start to behave like waves. So that means that they can interfere, and they have this kind of interference property. They can constructively and destructively interfere. And so instead of just getting 2 lumps of, so all the atoms or all the electrons going through these slits, you end up with several clumps of particles being detected at this screen here. So this is known as wave-particle duality. It just means that particles can sometimes behave like waves. Great. And it doesn't just happen for single atoms. There's been some beautiful experiments that have shown that we've been able to do this for molecules, so things constructed out of several atoms. And so here are some photos of some increasingly large molecules where they've been able to demonstrate the same thing. They fire these through the slits, and they show that these molecules can interfere in the same way that the single atoms or electrons could. And probably the most impressive experiment was from 2019, at least that I'm aware of, that had about 2,000 atoms. And this is the sort of the molecule here. It's actually starting to get quite big now. And what's really crazy about this is in order to prove that it was quantum, they had to resolve positions about 53 femtometers, so that's 10 to the minus 15. What does that mean? So take a millimeter and then divide that into a million chunks, and then take one of those million chunks and divide it into a million chunks, and that's now about the same scale that they had to measure this at in order to prove it's quantum. So one of the problems is as you add more and more atoms, it gets increasingly difficult to prove that these things are quantum. And a sort of related experiment, so these are mechanically compliant drums. So this is a bit of aluminium, and it can flex. It can flex up and down as a drum, and same with the other one. And here in this experiment from NIST in one of the national labs in the United States, they were able to create a superposition between these 2 drums. And the fact that these are different drums, in that instance, that superposition is something called entanglement. And so now you can see this is 5 micrometers, so this is like just 1 million times smaller than a sorry, it's only 1,000 times smaller than a millimeter. So we're seeing that quantum things can get bigger and still behave. Things can get bigger and still behave quantumly. The final experiment I want to show you was back from 2010, where they showed that they could entangle they could distribute entanglement over 144 kilometers. So now we're seeing some of these quantum effects at really large distances as well. And I think this leads to what I like to think of as the first law of quantum, and that is the bigger you make any quantum system, including quantum computers, the harder it is to observe and prove that it's behaving quantumly. And so this is one of the real challenges of the field. How am I going for time? Good. Okay. Now, that's not to say we don't have quantum technology already. Of course, we already spoke about transistors and computers. In order to describe how transistors work, we need quantum mechanics. So in some sense, this is what I like to call quantum 1.0. We kind of needed quantum mechanics in order to develop the technology, but it's not deeply quantum. So lasers are also useful in everyday life. In fact, the internet largely runs off fiber optic cables that are driven by lasers. And so our information is all transported this way. Of course, you can get LASIK and other medical procedures that use lasers. Maybe one that people might not be so aware of is atomic clocks. So here you use transitions in atoms to make very precise clocks. And this is actually how the global positioning system works. And that led me to navigate to this building correctly. So that's how Google Maps works under the hood. And there's other things too. So in the medical field, there's things like MRI machines, which depend on which use quantum principles to function. But really, we're interested in what I call quantum 2.0 technologies, and these are deeply quantum. So they really require quantum mechanics to work fundamentally. And I'd say there's three big pillars of quantum 2.0 technology. There's quantum sensing. And so maybe some of you were here for Professor David Simpson's talk, I think was it last week? Yeah, and so he spoke about quantum sensing. And so this is one of the pillars. We might be able to do, there might be interesting medical applications there or fundamental science applications. Another one would be quantum communications. Can we use quantum theory in order to change the way we communicate? This one's quite speculative at the moment. And then there's computation. And so I've intentionally drawn the computation pillar much larger, and that's because we think that ultimately quantum computers are going to have the largest impact out of all of these three technologies on society. So that's what we're going to focus on. Now, quantum computers are basically built out of these things called quantum bits. And we've already seen the classical bit. Remember, that was something that is either 0 or 1. Electrical engineers have made these really curious things that they called p-bits or probabilistic bits. And this is my attempt at trying to draw them in some way that's meaningful. And what does it mean? It means that they can be some random there's some randomization or probability to be in 0 or in 1. And so, for example, a coin might be an example of this. If you could change the bias of a coin if it wasn't fair, so a fair coin would be somewhere in the middle here. It has equal probability of being 0 and 1. And if you had a completely biased coin, 99% of the times it's head, maybe it would be somewhere down here. So this is what's called a probabilistic bit. These are used actually in machine learning. People are trying to build hardware that uses these probabilistic bits. So a quantum bit is neither of these. It's not a classical bit. It's not a random or probabilistic bit. It's something else. It's kind of difficult to describe without mathematics, but this is genuinely how we represent these things. So it turns out it's a sphere, the quantum bit. The top is this 0, and the bottom is 1. These weird symbols are what physicists use to write that. The probabilistic bit is just the vertical axis here, so it goes straight up through the center of the sphere. And so they're all the classical things, and the fact that you have a sphere rather than a line or these 2 points is the quantum bit. And how do you get this? It's because you can use this superposition. You can have a superposition of 0 and 1. And so the sphere represents all the possible superpositions of 0 and 1. Okay. How can you possibly build such a thing? Well, I'll give you 2 examples, and we'll go through a third one in a little bit more detail. So here I've got 2 boxes, and I'm going to stick a marble in one. So if the marble is in this, I'm going to say that it's 0, and if the marble is in this one, it's 1. And if the marble is in a superposition of being in 0 and 1, then that's a state that can't exist classically. So even this simple example here might sound a little bit ridiculous, but actually people like Professor Jameson have worked on these things in the context of storing single electrons. And so this is something known as a double quantum dot. So this is a kind of qubit that people try and build. Another one that might be slightly more familiar is an atom. So here we have the nucleus of the atom, and then these circles around here are meant to be the orbitals. And so we know that electrons can be in one orbital or another. And so a simple quantum bit would be, I have my atom, and the electron is either in the lowest orbital or in the next orbital. And so what are the quantum states of this? So that seems pretty classical. It's either here or there, but it could also be in a superposition of these two. So the electron could be in a superposition of the orbitals. Again, these are kinds of things that people actually do in the lab. If you're a little bit worried about this or confused, I highly recommend this. This is a simulation about quantum coins. It tries to explain the difference between bits, probabilistic bits, and qubits using an analogy with coins. It was developed by Ariel Paul at the University of Colorado. I was loosely involved in this a long time ago, so it's aimed at high school students. And so I highly recommend playing around with that if you want to think about that a bit more. Okay. So we've kind of seen something about qubits. So a classical computer manipulates bits. A quantum computer has quantum bits. And so what on earth is quantum computing? Well, roughly speaking, we know that computers are built out of matter or stuff. And so a classical computer or a quantum computer is bound by the laws of physics, so how much they can compute, what they compute. And so people use this idea to see if the weird effects in quantum mechanics could actually increase the speed of computation in any way. And so in particular, we found that and this is still the case today, for some problems, quantum computers can be faster than the computers that we use. The most famous quantum algorithm that we have was developed by this guy, Peter Shor, in 1994. And what he showed was that you could factor numbers easily. So for example, 15 times 3 can be, 15 can be factored into 3 times 5. And although that seems kind of useless, it turns out that a lot of our computer security is based on something called public key cryptography. And when you have two very large numbers and you multiply them together, it's very difficult to figure out what numbers you multiplied together in the first place. And so a lot of our encryption and secure transactions use this fact. And Shor's algorithm that he came up with in 1994 is so much better than classical algorithms that if we had a quantum computer today, we could crack many of the secrets that are out there in the world. And so this is one of the reasons why quantum computers got a lot of funding early on, because of the threat, the information security threats. However, I'd like to think that we've sort of advanced beyond that to think about, I think, more positive things. And so we think generally that they're going to be helpful for designing new drugs or potentially efficient fuels. Why is that? Well, I mean, drug discovery and things like fuels are roughly chemistry, and chemistry is atoms, and quantum computers can potentially simulate things like atoms and molecules more easily because they're quantum systems themselves. So that's the sort of intuition, and maybe it'll help discover new materials. So the big question is, how on earth do quantum computers function better than classical computers? And this is very difficult. I don't think there's an easy way to explain this, and I'm not sure that as a field we have a definitive way, but here's my attempt. How do quantum computers work? They do it by creating a superposition of all possible solutions. And then we use the same things that I've been talking about. We process the data to interfere the good solutions constructively, and then destructively interfere the bad solutions. And that's roughly how many quantum algorithms work. What you often hear in the media is that quantum computers work by trying all possible solutions, and that is emphatically not true. So anyway, I don't know whether this is illuminating, but that's the best I can do explaining how quantum computers work. What's crazy is that there's so many different kinds of quantum hardware. In fact, I think it's a zoo of quantum hardware. People are trying to build quantum computers out of mechanical components, like we did even before we had vacuum tubes in computing. People are trying to build quantum computers purely out of light, photons, and optics. I'd say maybe the three most popular hardware platforms for building a quantum computer is atoms. So here, this is an example of a trapped ion quantum computer. You can see these little blue dots up here. They're exploded views of atoms, and they're all in a line. Another one is semiconductors. So this is the same kind of technology we use to build ordinary computers, and then superconductors. So superconductors are electrical conductors. You cool them down below some temperature, and they no longer have electrical resistance. So these are probably the three most, they're the dominant platforms today. And if we tie it back to the classical computings, I'd say that there's so many different kinds of hardware at the moment, and it's unclear if any particular one will win. It's unclear if the hardware platform that's winning today will be the one that our grandchildren use, for example. But there's so much money and time spent on these different hardware modalities. I think it's important to emphasize that the research and development we're doing here is not wasted time and money, and that's because a lot of these hardware platforms will end up in medical technologies and other kinds of sensors. So I think that I'm really positive about the field as a whole, and it's going to take several revolutions similar to the semiconductor industry in order to get a functioning quantum computer. So I thought I'd give you a little bit of a peek into how a superconducting quantum computer works. This is the one that, say, the big companies are using at the moment. IBM, Google, and Amazon are building their quantum computers out of superconductors. So let's look at that. So here is, if you walk into a lab, this is the kind of thing you see. Over here is a gas handling system, and then this is a big aluminium rack, and this is the dilution refrigerator. So this gas handling system, the gas bottles are behind. It's got things like liquid helium, and it works on a similar principle to your fridge. So basically, this whole system here is going to cool down the internal part of this dilution refrigerator to very close to absolute zero. So absolute zero is minus 273 degrees Celsius. This cools it down to plus 10 millikelvin, so just a bit above absolute zero. Inside this can here is something that looks like a chandelier, perhaps. And if you go into sort of a lab in a physics department, they'll typically look like this. There's a few wires. As you go down in these sort of stages, the experiment gets cooler and cooler, and at the bottom is where you put, underneath this thing is where you end up putting the chip. In industry, they tend to look like this. Again, this is one of Google's. There's so many wires going down there because they need to control all their quantum bits. At the bottom is this puck-looking thing that's probably about this size, and the chip is in the middle, and so all of these are electrical connectors that send signals to the chip. You zoom in a bit more and you can see the chip, and actually if you hold one of these, sometimes you can see the devices. The devices are big enough to be seen with the eye at this point. This is when I was working for one of these companies. This is me helping wire up the fridge. You can get an idea of the size. I think this is Papa George standing on a stool, so he's a bit taller to get to the fridge, and then sort of give you an idea of scale. So I'm a theoretical physicist, and this was just me helping out and trying to learn a little about the practical side of things. And so this was posted to the company internal Slack, and someone else replied with this picture here. So it tells you how much they trust me with these things. So yeah, maybe you shouldn't listen to what I've got to say. Okay, so this is a bit of promotional material from IBM, but the reason why I want to play it for you is it gives you an idea of what a lab is like in one of these big companies that's trying to build a quantum computer. And there's a bit of audio associated with it, and probably 85% of quantum computing labs all around the world sound like this. So this is the kind of sound of a quantum computer, and I'll also point out some of the sort of steampunk aspects of quantum computing. So first, you've got these big copper wires here, and they actually help thermalize these different layers. So they help, conduct the cooler temperatures down. But let's see if I can get it to play. So this is the gas handling system and the pulse tubes on the previous slide making that noise.
Welcome to Sounds of IBM.
So the thing I want to show you is their control electronics racks. So so I think that's coming up. Where is it? It's very steampunk here. So here's the control electronics racks. Look at these wires. This is just to control, like, I don't know, 30, 40 qubits. So it's kind of, this is just on YouTube, so you can look it up. It very much looks like these old computers from the 1940s and 1950s. So I think we've got a long way to go in the technological development. So if you zoom in a bit more on that chip, there's 5 qubits on this chip. I think this was from around 2012, this device, when they made it, so only 5 qubits. And there's a bunch of other control electronics around on the quantum chip to help them prepare interesting quantum states, execute interesting quantum algorithms, and then read out the information. So what on earth are these qubits? They're superconducting qubits. They're built, so the way they build them is they have to develop a new electrical element. So this is not a transistor, but it's the superconducting, I don't know if it's equivalent, but it's a new element that they use to build qubits out of it. And so how do you do that? You take 2 bits of superconductor and you put a very thin insulator between them, so you butt it up, and then you cool it down to very close to absolute zero. And a weird thing happens is electrons are no longer the thing that flow through the circuit. It's actually pairs of electrons, and that should seem weird to you because if you remember, electrons are negatively charged, so if you put 2 negatively charged things close together, they should repel. And so weirdly enough, these Cooper pairs are actually pairs of electrons that are bound together, and there's some cool physics to do with the crystal lattice of the material vibrating in certain ways to, hide or not hide the positively charged lattice of the atoms that effectively make these Cooper pairs seem as if they're bound together. So what happens is the Cooper pairs propagate in this superconductor, and then they tunnel through this very thin insulator. And so this is a new kind of electrical element, and the fact that it's using tunneling also gives you a clue that this might be a quantum device, or somehow quantum. And so this is called a Josephson junction, and it's given this weird electrical symbol. And this is basically how all superconducting qubits are built. So they put a Josephson junction, this tunneling device, in parallel with a capacitor. Remember, capacitors are things that just store a little bit of charge to plates that are separated, and they have positively charged things here and negatively charged here. And what's weird is when you cool this electrical circuit down, is it starts to have discrete energy levels in the same way that an atom has discrete energy levels. Okay, there's no nucleus here, but you can see that there's a ground state, and then there's a first excited state, and a second excited state, and so on. And so this is the energy levels of this electrical circuit. So that maybe if there's electrical engineers, hopefully that seems weird to you, and so that you can have quantized electrical circuits. Okay, so using these transmons or artificial atoms, IBM has gone over the last 10 to 15 years to build larger and larger devices. And so this is one of their devices that has about 120 qubits. The dots here represent the qubits. The lines represent the ways the qubits are connected. So it's a little bit annoying at this point in time. So if I wanted to, say add the value of this quantum bit with this quantum bit, I have to sort of swap them around in this weird geometry in order to get them to talk to each other. But that's kind of the stage we're at now. And broadly speaking, most of the big companies have somewhere between 100 quantum bits and under 1,000, so maybe like 900. So if you can just log on to IBM and create an account and access their quantum computer somewhat for free. It won't be their best quantum computer. How that works is you write some code on your laptop. It gets sent over the internet and to their control electronics rack. That gets transmitted down to the base of the fridge. That is the input to the circuit and the program that gets executed. The quantum measurement results get sent back to you via the internet. And so this is essentially how all of the quantum computers work today. Unfortunately, the problem is quantum computers are noisy, and the biggest problem is something that should be very familiar to most of us. It's to do with friction. And so maybe the best demonstration, if you've ever seen one of those pendulum clocks, you know that eventually they'll stop swinging, and one of the reasons they stop swinging is because of friction. And so this is basically losing energy, and so we call this energy relaxation. Another, if you think of a quantum system, such as an atom, an electron can decay from one orbital to another by losing energy. So in this case, it's emitting an X-ray photon. And so this is another example of energy relaxation. And this is one of the key problems in quantum computers and why we don't have large quantum computers today. So let's see if I can get through this before too long. If we want to benchmark how good are the devices that we have today, there's a great benchmark that IBM has come up with, which essentially counts the number of quantum bits, so represented by the wires in this direction, and then you run some weird-looking circuit. So this is some logic gate or some program on the quantum computer. And what they decided to do was benchmark it in the following way. They want to run a square circuit, so they want d quantum bits, and they want to run a depth d circuit. And then looking at the output of the device, they want to be able to prove that the output is quantum. It couldn't have been produced by a classical computer. And so it's actually a very rigorous test. And to date, the world record is from this company called Quantinuum. And they were able to prove that 23 of their quantum bits are behaving fully quantumly. I should say that their devices are limited to about 20, at the moment, 25, 26. So they've kind of reached capacity at this point, but they have the best device in the world. If you look at the superconducting qubits, so this particular device here has 156 qubits, and IBM was only able to show that 9 of those are quantum, so coherently behaving. So even though they've got a lot larger device, it's not behaving as a whole quantumly. Part of it is quantum, part of it's classical. So that's a real challenge to build a quantum computer. So the major impediment to building a quantum computer is really noise at this point. And so there's 2 approaches we need to take in order to fix that: improve the hardware and use something called quantum error correction. And so this is basically the last thing I want to tell you about. So how do we fight noise? We have to come up with ingenious ways, and this is called, actually I'm just going to tell you about classical error correction, and then there's a quantum version of this. So suppose my wife was trying to decide whether to come to this talk or not, as she was earlier today. And she's going to communicate the information to me by sending either 0 or 1. So 0 means yes, I will come, and 1 means no, I won't come. And so she sends this 0 to me. It goes through this fiber optic cable, and unfortunately it has an error. And in this case, it flipped to 1. And in general, it could have happened the other way. You could send a 1. And so you can kind of draw this as a tree diagram. There's some possibility that the 0 gets transmitted perfectly, and then some possibility that the 0 gets, some probability that it gets flipped into 1. And similarly, the 1 could have the same thing. So 1 could go to 1, and occasionally it could get flipped. So these are the kinds of errors that we worry about. One way to fix this is introduce redundancy into your message. So let's do that. So instead of just sending 0 and 1, why don't we repeat the message? So instead of sending 0, we'll send 0, 0. Instead of sending 1, we'll send 1, 1. So I'm going to, let's do that. So these are the messages. I'm going to send 0, 0 and 1, 1, and these things are kind of junk. So now what happens is if I want to send 0, 0, and this bit here flips, it takes me to this state here. So that was not one of our agreed upon messages, so it doesn't make sense. Similarly, if the most significant bit flips, this is not one of our agreed upon messages. So if I receive 0, 1 or 1, 0, I can just say, well, that's a junk message. An error must have happened. So I can detect an error, but I can't correct it with this. So let's introduce some more redundancy. So now we're going to use 3 bits. So this is, I actually realize there's a mistake here. This is meant to be the numbers 0 through 7. And actually, there's only 6 things Wait, is that 1, 2, 3, 4, 5, 6, 7? Okay. I think 1 is missing here. It should be 1, 1, 0. Anyway, we'll do the same thing. We'll communicate with 0, 0 and 0, 0, 0 and 1, 1, 1. So let's do that. Now, if one error happens, so suppose we send 0, 0, 0, it will take us to these states. So if this bit flips, it'll take us to here. If the middle bit flips, it takes us to here. And if the most significant bit flips, it takes it to here. And similarly, if we wanted to say no, we flip along these 3 edges. And the important thing here is that these error states no longer overlap. So if I get any of these 3 states, the ones in green, then I can correct back to 0, 0, 0. And if I get any of the ones in purple, I can correct back to 1, 1, 1. And so this is an example of an error correcting code, and it can tolerate 1 error. If there's 2 errors, it can't tolerate. You can design bigger codes that can tolerate more errors. So one of the points here is that you need to make the code big enough to tolerate errors. And this brings us to Google's result. And like I said, I think this is one of the most important experiments in the history of quantum computing, and it was just published this year in, I think, January of this year. And it's kind of overwhelming, so let's just restrict down to the most important information. And to give you an idea, I think this is probably the most important experiment in the last 20 years of quantum computing. So zooming in on 2 parts here, what they've got over here is this is a grid of their quantum bits. We saw IBM's version of this earlier. This is Google's. And so they've got some data qubits, some qubits they measure, and some qubits they use for other reasons. And they're going to take grids of these qubits. So they're going to take a 3x3 grid, that's a 3x3 grid, or a 5x5 grid, I don't know if that's 5, or a 7x7 grid of these qubits. And they're going to encode them into a quantum error correcting code, so something like the code we saw, but for quantum systems. And they were able to show that if they used the 3x3 grid, we had some error rate. And when they went to a larger grid, so more qubits in the code, the error rate went down, so it got better. And when they went to the 7x7 grid, it got even better. And so this is the first time in the history of quantum computing we've seen the devices get better as we make them larger. And what's crazy to think is in order to build, to run a quantum algorithm that we'd like to run, we think that we're going to need to have 300 physical qubits for every 1 logical or virtual qubit, which is kind of wild. And so that's the current estimates of where we're at with quantum computing. So if you think these companies have around 1,000 qubits, then that means roughly, in reality, if we use these quantum error correcting codes, they really have like 3 qubits or something like that. Okay, so I think, broadly speaking, the next 10 to 15 years of quantum computing is going to be focused on fighting noise, and there's 2 ways to do that. One is designing new qubits that are more reliable and improving fabrication techniques, so how we build the devices. And then the other one is going to be learning more and more about error correction. So I think, broadly speaking, that's what is happening in the field of quantum computing. And I think I might wrap up with that. So thank you so much.
Josh, thank you very much. And isn't it wonderful to have a public lecture where you hear from a paper that was just published a few months ago highlighting a fantastic breakthrough. So thank you for that. So given that our refreshments are waiting for us over in the library, I think we've got time for 2 questions. I might take one live from the theatre and one live from the iPad. So is there someone with their hand up right up the very back, second back row?
Hi, Josh. Thanks for the talk. My name's Dean. I'm a former student of the school. You mentioned earlier in the talk that one of the main funding sources and applications early on in quantum computing was for breaking cryptography. In the present day, what are the major funding sources? Who are the main spenders of that funding? And for what application, if you can talk in relative terms? Yeah,
it's a good question. To be honest, I I'm going to tell you based off feels, not based off fact. But I think historically, defense has been the largest funder of quantum computing, that's largely come from the US. And to first approximation, quantum computing is done in the US, and you can more or less ignore the rest of what happens in the world. That's not exactly true. In Australia, we've got important contributions, but the sort of volume of money that comes out of there. But there are other things like the National Science Foundation, the Australian Research Council have made really important contributions. In Australia, for example, David has been funded continuously since, 1999 by the Australian Research Council to develop quantum computers. So, the progress we've made as a country has been incredible. I think that's changed. I think now industry, places like Google and IBM are the dominant funding sources for quantum computing, and they have basically overwhelmed any investment from any other place. Would you agree? Yeah,
absolutely. When looking at the very first classical computer, it was in a university laboratory, and it had 1,000 vacuum tubes, as you probably know. But it eventually moved out of the university laboratories into industry. And I agree. The quantum computer is following a very similar path to the classical machines.
It is, yeah.
Yes. So it seems that the error correction is not working on the internet questions, so we don't have any questions online. So what I'd like to do now is just remind you that we've got 2 more July lectures to go. The last one will be on the 1st of August. But the one next week, I specifically invite you to come back for. Dr. Danny Holmes will be talking to us about the quantum century, unlocking the universe's secrets and shaping the future. Please come back next Friday to hear what Danny has to say and to continue to celebrate 100 years of quantum mechanics. So please thank Josh again for a wonderful and up-to-date and interesting lecture.